So I'd like everyone to kind of think back to the bygone days of junior high science, which is probably for many of you the last time that anyone ever asked you to balance a chemical equation. For some of you, you're remembering well and clear that it was something that you did. You may have tolerated it. There's a really good chance if you remember it, you probably don't have really great memories of it. Or it may be possible that you have repressed those memories because the brain tends to kind of get rid of traumatic experiences to kind of shelter and protect us for the rest of our days. Typically when people come to me in chemistry and they have tried balancing equations, two reasons why it didn't stick. Reason number one is because nobody ever bothered to tell you why you're doing it, why you had to learn how to balance an equation, what the whole point was. The other reason why people have not really enjoyed or gotten much out of balancing equations is because they've never had me teach them the best way to do it. After today, I'm going to teach you not only why it is that we balance equations, but an absolute no-fail method for doing it. If you already can balance equations pretty well, that's great. After today, you're going to be even more betterer at it. All right? So, just as a quick recap, we've been looking over the last few days at chemical reactions, and what's the collective word that we give what we're starting with? Reactants. Excellent. Okay. I'm not sure. I don't think I want to try. Oh, you know what? I think I might try and write that. Let's find out. Nope, I don't think I'm going to. What do you call the collective group of stuff that you end up with?
Products.
Products. Excellent. Now, any of the chemical equations that we have looked at, any of the reaction types that we've been studying, any of the reactions that you performed in lab, in every case, what you're doing is you're taking certain ingredients, you are scrambling them around, and you're using them to put together new things. You are not at any point making new atoms. You are not at any point destroying old atoms. It is a lot like Lego. Reed, what is the plural of Lego?
Lego.
That's right. If I have 2 Lego, if I have 12 Lego, I don't say Legos because then Lego nerds will tend to get huffy. How many of you have ever played with Lego? There's like 2 hands. None of the rest of you have played with Lego like ever? Okay. All right. So you know that the way Lego works is I can have like a Lego spaceship, and I can take those bricks and I can take it apart and I can use those same bricks to build a dinosaur or to build a castle, right? In the process of unbuilding or rebuilding, I'm not actually taking any bricks and chopping them up or melting them down or destroying them. I'm not pouring new plastic to create new bricks. All I'm doing is just reorganizing the bricks I already have. It's the same thing for any chemical reaction. Okay? In short, whatever crap you start off with is going to be the same crap you end up with. Okay? Or, slightly less, of course, of a term. What you start with is what you get. It's just going to look a little bit different. Up until now, we've been concerned with examining the reactants and the products themselves just to make sure that those are legit compounds, and then also saying how it is they're changing. But we also have to be able to keep an account of where every one of those atoms goes when we have a chemical change. And so we have to honor the law of conservation of matter, also sometimes referred to as the law of conservation of mass, which simply says that during a normal chemical reaction, atoms are not created or destroyed, they are just rearranged. So I'm going to introduce to you today what I like to call the King method for balancing equations. And it is so ridiculously simple. Anybody can do it, and there is no way you can go wrong using these steps. Okay? So I'm going to ask you to kind of keep an open mind and just kind of work along with me, and we'll see how you feel about things toward the end of class. Okay? Let's take a look at the paper that I gave you. Okay, this fella right here. And we're going to take a look at equation number 1 right there. And then we're going to follow our steps in the King method for balancing equations. So let me grab one of my popsicle sticks. And Samantha, would you please read out to us what step 1 in the King method is? Okay, so that's going to be what we do. We're going to start with this equation. We're going to take our own paper. We're going to rewrite it exactly as it's written. Okay? Little blank out in front and everything. Possibly the most important part, because if you don't copy it down correctly, then there's no way you can solve it. So always double check to make sure you've got it down right. Okay? Abby, what is step 2?
Draw a line down through the yield arrow, extending it a few lines below the equation.
Okay, so let me demonstrate for you. So I find my yield arrow in between my reactants and products, and I'm going to draw a line, and I'm going to drop it down a good bit, at least a few lines underneath. Now let me tell you what it is we just did here. It may look like a line on a piece of paper, but what we've done here is we've actually built a fence. We have constructed a wall. We have erected a barrier. What is the purpose of a fence or a wall?
To
keep things separate, to keep things out or to keep things in, right? And so what we've got right here is a boundary. And what this means is that anything on the left side of this wall stays on the left side of this wall. Anything on the right side stays on the right side. Any changes that happen over here have no effect on what happens over here and vice versa. Everybody cool with that? We've built a fence. All right. McKenna, what's step 3?
Just each kind of atom use the same rest on both sides. Atomic groups are okay to for them to change.
All right. So what I'm going to do now is I'm going to look and see what elements are present on the left side of my wall. What do I have here? I have nitrogen and I have hydrogen. I'm going to use the same exact list on the other side of my fence here in the same exact order. Now, let me throw another metaphor at you. What we've just done right here is we've just built a scoreboard. What's the purpose of a scoreboard? To keep score, right? I'm going to ask some really obvious questions, but here's another one. Is the whole purpose of going to a game, whether it's basketball or football or soccer or volleyball, is the whole purpose so that you can sit and watch the scoreboard? Why do you go to a game? To watch the game. So would it be safe to say that the game is more important than the scoreboard rather than the other way around? I agree. So this right here is our scoreboard. This up here is the field, and these are the players. So we're watching what's going on the field, but we're keeping track of it down here on the scoreboard. Ruby? All right. Emily, what's step 4?
Write the total number of each kind of atom decided simply for both sides.
All right, excellent. So looking just at the reactant side here on the left, how many nitrogen atoms are on this side of the wall? Okay. How many hydrogen atoms? Great. Now, looking at the other side of the wall, how many nitrogen atoms do I have over here? 1. How many hydrogens? Great. Now, here's where the sports metaphor falls apart a little bit. Typically, if you're in a sporting event of some kind, the whole point is to get a bigger score and win the game, right? I mean, they tell you it's, because it's fun and it's not important whether you win or lose. That's bunk. It's all about whether you win or lose. You want to have the higher score. You want to be the winners. So this is kind of not like sports because the whole point of this game is you want it to be a tie. At the end of the game, you want both sides, both teams, to have tied scores. So what I'm going to do now in my next step is I'm going to attempt to alter the game up here in such a way to where I've got a tie game every time. So Haley Jones, would you please read for us step 5?
balance each kind of atom one at a time by changing the coefficient. Numbers in front of each reactant and solvent. If you break something, referencing something else, substitute.
Great. So did you know, you know what? I didn't copy this down right. There's supposed to be a blank right there. Did you know that there is something in those blanks? There's actually an invisible number in there. Do you see it? No, you don't. It's invisible. Pay attention. If you could see it though, what invisible number would you see in those three blanks? Any guesses? It's an invisible number 1. Do you see it now? That's exactly right. You're paying attention. It's still invisible, but there is a number 1. What the game currently tells me is that 1 molecule of nitrogen will react with 1 molecule of hydrogen to make 1 molecule of ammonia. The scoreboard tells me that's not true because it's not a tied game. So what we're going to do is we're going to look at our scoreboard and we're going to fix what's broken here. Now there's not a wrong way to do this. You can choose to fix the N's first or you can choose to fix the H's first. Either way, you're going to get there. So for the sake of argument, let's take a look at our nitrogens first. They're broken. We need to fix them. So I look and I try and figure out which side do I need more hydrogen on, the left side or the right? The right. So I look down on the field on this side of the wall and I find nitrogen. There he is. And I'm going to change that invisible number 1 to something else in order to tie my nitrogens up. So what number needs to be in that blank? So I'm going to put a 2 in that blank. I'm sorry, my blank is kind of messed up there. Now what that does is that changes my score. So I now have 2 nitrogens. It also changes my number of hydrogens. So I've got 2 times 3 or 6. So my nitrogens are now tied. I just need to go back and fix my H's. Where do I need more H? Left side or right side? Left side. So I'm going to go find him on the field on the left side. There he is. Looks like he comes in packs of 2. So how many packs of 2 will get me 6? So I put a 3 here. 3 times 2, it's 6. Now I look at my scoreboard. I've got a tie game. And I'm done. Except there's one more thing I probably want to do. I don't have to do it. Remember this invisible number 1? Do you see it? You're going to make it visible. You don't have to, but it's a good idea too. For a couple reasons. One, if I'm looking over a paper full of these problems and I see blanks, I panic and think, gosh, did I finish that one or didn't I? And I waste time going back to see, did I really get that done or not? The other reason is, what we have here is a ratio of 1 to 3 to 2. It tells me that 1 molecule of nitrogen will react with 3 molecules of hydrogen to give me 2 molecules of ammonia. If I can reduce that ratio, I have to reduce that ratio. Can I reduce a ratio of 1 to 3 to 2? I cannot, because you can't reduce the 1, right? So I know I've done that correctly. So now I go back to my paper, and I go ahead and fill in 1, 3, and 2. And I'm done. Criticisms at this point would include something like, gosh, Mr. King, that seems awfully complicated just to do such a small thing. Or, you're going to end up eating up a lot of paper if you keep doing this. I would answer both of those by saying, yes, it does seem like an awful lot to do, but once you're dealing with a lot more complicated reactions, you're going to want to be able to use the space and follow the steps. 2, you're not really killing trees so much as you are helping some poor logger to put his kids through college. Okay? So it's all right. These particular trees that were dead a long time before you got here, they're not going to feel a thing, so use them up. Are there any questions before we look at some more?
Can you do all these together?
We can do a few of them. Quite a few. Okay? But we're going to keep using the same kind of system here, and we're going to see how that works for us. Okay, so drop down and look at number 2. What's my first step again, Reed? I'm going to rewrite the entire equation. Okay, Grady. So let me fold this to get out of the way. I'm going to rewrite my entire equation. KClO3 yields KCl plus O2. And I need to be sure and put my blanks. By the way, what kind of chemical reaction is this? Decomposition. Very good. Okay, so now I've got it copied down. That's step 1. Avis, what's step 2?
Draw lines through the gold
build a fence. Okay, so there's my fence. I've given myself some space underneath to work. Great. Shiloh, what's step 3? Okay, so Shiloh, what atoms do I have here? Uh-huh. Great, and I'm going to do the same list in the same order on the other side. Does it matter what order my list is in? Not really, but I do want to keep it the same because it's going to make it easier to compare. Shoot.
Did you leave KCL as one thing since it saves two others?
You could, in this case. KCl is not, in and of itself, a polyatomic. Okay, but other polyatomic ions you absolutely can. If you wanted to leave KCl together here, you could. It's a little unorthodox, but it would work. Okay. Erica, what's my next step? Okay, so Erica, on the left-hand side here, how many Ks do I have? Okay, how many chlorines? How many oxygens? Great. Okay. Haley, on the right-hand side, how many Ks do I have? Okay, how many Cls? How many oxygens? Great. Okay, so going on to step 5, I'm going to fix these one at a time. Well, what if they're not broken? Then I don't have to fix them. What if by fixing something I accidentally break something else? Is that okay?
Yes.
So long as I go back and fix it again. So what's broken here? The O's are broken. So how am I going to work that? Because over here they come in packs of 3, and over here they come in packs of 2. 2 packs of 3, 3 packs of 2. So I'm looking for a common multiple like 6. Great. Okay. So how would I get 6 oxygens on the left side? Put a 2 here. Now that effectively doubles everything, so that gives me 2 of those, 2 of those, and 6 of those. And how do I get 6 oxygens over here? Put a 3 in front of the oxygen here. That gives me 6. All right. So now I need to fix my K and my Cl because I broke them. How do I do that? Put a 2 right here. So 2 potassiums, 2 chlorines. Can I reduce 2 to 2 to 3? Then I'm done. So I'll go back to my paper and I will fill in 2, 2, and 3. Questions? Do they stay that easy? Actually, for the most part, yeah. There's a few tricks that you do learn the more of these that you work, but for the most part, it is just that easy. Let's take a look at number 6. Okay, you've heard the directions a couple of times. So what you tell me, what do I need to do? I can't do that yet.
Oh, write your equation.
There you go. Okay, I'm going to zoom out just a smidge there. Okay. All right, so now I've got my equation copied over. What's next? Now draw my line. Okay. Now what? Set up my scoreboard. Now, before I do that, I'm going to notice I've got a polyatomic ion right here, SO4. And if I look on the other side of my wall, I've still got the same polyatomic. It doesn't ever fall apart. It stays together. So when I'm making my list, I could list sulfur and oxygen separately. But like Haley was doing a minute ago with the KCl, since they never separate, I could just leave them together and list them all as a single ingredient. So I could go aluminum, bromine, potassium, and groups of SO4. And then I could do the same list on the other side. It might make things easier, it might not. It usually does. Okay, so now what? Write the score. So what's on the left-hand side? What's the score for aluminum? Bromine? Potassium? SO4 groups. I have one SO4 group. Good. Okay. Right-hand side, how many aluminums? Bromines? Potassium? SO4 groups. So what's broken? Everything, right? It doesn't matter where we start, so where would you like to start? Cool. Where do I need more, left or right? Left side, so there's aluminum on the field, so what needs to go in that blank? We're going to put a 2 there. Change our invisible 1 to a visible 2. That gives us 2 aluminums, 6 bromines, 2 times 3. Okay, so aluminum's fixed. What next? Why not? Where do I need more, left or right? Okay, so there's bromine out on the field. What needs to go in that blank? 6. That gives me 6 bromines. It also gives me 6 potassiums. Okay, 2 down. Where 2? Okay, the potassiums. So I need more on the left. They come in packs of 2, so how many packs of 2 do I need to get 6? Okay, put a 3 here. That gives me 2 times 3 or 6 potassiums. It also gives me 3 groups of SO4. Oh, hey, guess what? We fixed it. Just come over here and turn my invisible 1 visible. Can I reduce 2 to 3 to 6 to 1?
No.
Nope. So I'll come back to my paper. I'll go ahead and fill in 2, 3, 6, and 1. And I'm done. It's a great place for questions if I've been moving too quickly. Okay, how are you feeling about this?
Are we gonna have any meetings?
Sometimes. Sometimes we do. Okay. Anybody else? Okay, let's see. Let's take a look at number 8. What kind of reaction is number 8? It's combustion. Very good. You've got a hydrocarbon reacting with oxygen to get CO2 and H2O. All right, so you tell me, what do I do? Okay, step 1, copy it down. So C3H8. This is propane, by the way. All right, I've got it copied down. What next? Okay, go ahead and build my fence. List my players. Who's playing? All right, carbon, hydrogen, oxygen. Show. All right. What's the score so far? Left side. 3 carbons, 8 hydrogens, 2 oxygens. Right side, how many carbons? Hydrogens? Be careful, oxygens. Good job. Because there's 2 there and there's 1 there, and the score keeps track of all of them. All right, so what would you like to try and fix first? Fair enough. Okay, so I need more carbon on the left or the right? Okay, so there's carbon, so what needs to go in that blank? Okay, now that gives me 3 carbons. It also changes my oxygens. I've got 2 times 3 plus 1. Good. Okay, carbon's fixed. Where to now? Okay. Oh, hey, you know what? I kind of forgot to mention this. Take a look back over on the slip. And Reed, would you read the second hint that I have written there?
Try saving oxygen for last, especially if it's present in several reactants and products.
Yeah. So sometimes, like you see right here, see how oxygen shows up in multiple places? That happens a lot. And when that happens, try fixing everything except for oxygen. And sometimes oxygen will just fix itself. But if I tried to fix oxygen first, as soon as I changed something else, it would break it again. So that's why oxygen being saved for last is our best bet. So looking back at hydrogen, I need more here. They come in packs of 2, and I need a total of 8. So how many packs of 2? Okay, good. That gives me 8 hydrogens. Now let's recount our oxygens. We had 6 plus 4 is 10. Now we fix our oxygen on the left-hand side. How can I get 10 oxygens out of that? 5 there. 5 times 2 makes it 10. My scores are tied. And I'm done. How easy is that? Not bad, right? Let's look at a few that might be, well, let's go back up to number 5. Oh, let me get my answer on here real quick. That was 1534. Okay, so problem number 5, we've got PbOH2 plus HCl yields H2O plus PbCl2. So we'll start like we always start by copying down our equation just like it's written. Okay, now I'll make my fence, build my wall. Now I'm going to notice, because I'm always on the lookout for polyatomic ions, I do have a polyatomic ion on the left side, right? I've got this OH group, this hydroxide. Do I have the OH group on the right hand side? Except, what if I do? Do you recall when we talked about sometimes if you got a reaction where one substance has OH and the other substance has H, they get together and they make water? That was that 6th kind of reaction. What is that? Acid-base reaction. Avis, would you mind reading the 3rd hint at the bottom of the slip?
Try writing water as H, OH, hydrogen, hydroxide, and balancing simple acid-base equation.
Excellent. Now, it doesn't always help, but sometimes it helps tremendously. If instead of thinking of this as H2O, if I think of this as HOH, then it might make it a little bit easier to balance this one. So I'm going to list all my players. I got lead, I have hydroxide ion, OH group, I've got free hydrogen, and I've got chlorine. Same list on the right. And again, sometimes this makes it easier, sometimes it's about the same. Let's get the score. On the left side of the wall, how many leads do I have? Groups of OH? H's? Chlorines. Okay, over on my product side, how many leads? Groups of OH? Free H's? And chlorines. Okay, so what's broken on my scoreboard? Okay, which one would you like to fix first? OH, cool. All right, so where do I need more hydroxide, left or right? Okay, so how am I going to get that? The 2 right here. That's going to give me 2 free hydrogens and 2 groups of OH. OH is fixed. Now what? I can go back and fix my hydrogen. All right, so I need more on the left, so what needs to go in that blank? Okay, that gives me 2 hydrogens, 2 chlorines, and oh my goodness, I'm done, right? Let's go through and turn my invisible ones visible. And we're finished. Can I reduce 1 to 2 to 2 to 1? Then we are done. Questions? How are y'all feeling about this on a scale of 0 to 5? Show me fingers. And some 4s. 4, 5, 4, 6. You might want to have a doctor look at that. 4, 5. Okay, good deal. All right. So here's the fun part of the show where I put everybody's name in the bucket, and whoever I draw gets to pick the next question we're going to work together. Okay? So y'all start looking at those, and I know how everybody's eyes go straight to the bottom of the page or start looking for the longest, most complicated looking one. So let's see. Shiloh, what problem would you like us to work together? There's no wrong answer. Number 12. All right. All right, so on number 12, I've got sodium and water, and I get sodium hydroxide and hydrogen. Okay, cool. So first step, I'm going to recopy it. I'm going to get my good pen. Now, do I have any polyatomic ions here? I do.
So we had to rewrite the
I could, or I could leave it like it is. Would you like us to work it both ways? It doesn't really matter. Okay, you say switch it? I think that's fine because we've got an H and we've got an OH here, so let's rewrite this as HOH, and let's see what happens. Okay, so I'll build my fence, list my players. I got sodium, I got free hydrogen, and I have hydroxide ion. I'll do the same thing over here. On the left, how many sodiums do I have? Free hydrogens? Hydroxides? Groovy. On the right, sodiums? Free hydrogens? Hydroxides? Okay, so what's broken? Free hydrogen is broken. So I'm going to do that, make it easier to remember he's the thing. So how do I fix my hydrogens on the left? Put a 2 right here. That's going to give me 2 of those. It's also going to give me 2 of those. So I broke my hydroxide. How do I fix it? Put a 2 right here. That fixes my hydroxide, but oh no, I broke my sodium. Now what? Okay, put a 2 right here. That fixes my sodium. Tie game. And I'm done. That was point number 12. Fantastic. Avis, would you pick us out another one? 18, she says. She's like, mwahaha, that looks big and mean. Okay. Let's look at number 18. Whew, that's complicated, right? Especially if I have it off camera, it's really hard to see. There we go. Okay, so let me copy this down. HNO3 plus NA. I'm taking nitric acid and I am mixing it with baking soda. It gives me sodium nitrate, probably dissolved in water, plus water, plus some carbon dioxide gas. So I'm going to get some bubbles. All right. Fantastic. Next step, I'm going to find my arrow, build my wall. Now, are there any polyatomics here? Well, HCO3 is, but notice how it doesn't stay together over here? So I can't use HCO3. Are there any others? NO3. Nitrate ion, that totally stays together, right? Okay, I think we're good. Let's go ahead and list our stuff. So we've got hydrogen, NO3 group, sodium, hydrogen, carbon, and oxygen. That's a long list. A lot of players. Let's do the same list over here. Okay, so on the left side of the field, how many free hydrogens do I have?
2.
I got 2 of them. Good. Okay, NO3s? Got 1. Sodium? Wait a minute. I listed free hydrogen twice because I'm an idiot. Okay, let's get rid of the second one. How many carbons? 1. How many oxygens that are not part of NO3? 3. Good. On the right side, how many free hydrogens? 2. How many groups of NO3? Okay, how many sodiums? Uh-huh. How many carbons? And how many free oxygens? Huh. I'm noticing something. Tell me if you see it. They're already equal. It's already a tie game. So all I have to do is go through and turn everything visible. Way to pick 'em, Avis. That's all right. Sometimes that happens, and it's.
I knew somebody was gonna pick it because you said that they get the biggest one and they do every time.
Uh-huh.
It
You know what?
always ends up being the easiest. Every
You know,
time we do it.
not always. Sometimes these are already balanced, but see, we verified it. We know for a fact it's already balanced, and we didn't know that just to look at it a minute ago. So we have not wasted our time here. Speaking of wasting our time, I think we could probably work at least one more. Reed King, would you like to pick out one for us?
Alrighty. Number 15.
Number 15. Excellent choice. Ah! 15 should be a very familiar equation to you if you've had biology. What is it? Yeah, that's photosynthesis. So let's do a little photosynthesis. We got CO2 plus H2O yields glucose, C6H12O6 plus oxygen. If we took this and turned it around backwards, what kind of reaction would we have? Cellular respiration, but out of our 5 classes over there, what kind would it be? If you flipped it around, you've got a carbon, hydrogen, oxygen compound. Do it. Our products would be CO2 and H2O. It would be combustion if we did it backwards. Because remember, cell respiration is just combustion on a very, very small scale. So, let's go. What do I do next, y'all? Okay. Who are my players today? Groovy. All right. What's the score on the left side?
1 carbon, 3 oxygen, and 2 hydrogen.
Okay. On the right side, how many carbons? 6. How many hydrogens? Careful, how many oxygens?
8.
All right. So, I think it's probably going to be safest to save what for last. Don't you think? Because it's everywhere. So, do we want to fix carbon or hydrogen first?
Carbon.
Fair enough. Where do I need more, left or right? Okay. There's carbon on the field, so what goes in this blank? Okay, that gives me 6 carbons. That also changes my oxygens. I've got 2 times 6 plus 1. 13. Okay, carbon's good. Now how about hydrogen? Who needs more, left or right? Okay, so there's hydrogen. He comes in packs of 2, and I need 12. So what goes here? Another 6. So that gives me 12 hydrogens. Recount my oxygens. I had 2 times 6. That makes 12. Plus another 6. That makes 18. So now looking at the right side, I still need to fix oxygen. Now notice oxygen is present here, and it's present here. Which one of those do I want to mess with? Right. What happens if I mess with this one? Right, it breaks everything. So, if I need 18 oxygens total, 6 of them are going to come from right here. So if I do a quick 18 minus 6, what am I left with? That means that 12 oxygens have to come from right there. So what goes here? Another 6. So that's 12 plus 6, 18. Can I reduce 6 to 6 to 1 to 6? I could if it wasn't for that pesky 1, right? So I am done. Oh gosh, I think that's probably going to be a pretty decent place to call it quits for the day. Tomorrow we're going to look back at some of the equations that we classified on our own. And also remember tomorrow, your lab write-up, if you didn't get that handed in, that is going to be due. So be sure that you get those finished up and turned in to me.